Hello everyone. Welcome to this new lecture of CT509. So we are maybe 3 weeks in the remaining time. But first, let me start by today by kind of summarizing what is the content that I wish to cover in the remaining part of the semester. This is my wish list. I don't know how much of it I will be able to actually do justice to, but anyhow, so this is what I'm thinking of, that today I'll cover the topic of non-orthogonal multiple access, which, as you know, is one of the key technologies, multiple access technologies planned for 5G systems. So I have some material on NOMA today. Maybe next lecture on Wednesday also I will continue on NOMA, but that time maybe we'll just review some papers that kind of form the basic technology of the NOMA. So it might take 1 or 2 lectures to complete the NOMA topic. After that, I wish to spend some time on the LDPC codes, and specifically the iterative belief propagation decoding. The reason is because in NOMA, the methodology that is used relies kind of heavily on some of these belief propagation algorithms, which are also known as message passing algorithm, or MPA. And in general, this message passing algorithm on the LDPC coding graphs, by the way, the LDPC codes are probably one of the simpler to understand type of codes, in my opinion, where both encoding and decoding structures can be conceptualized in terms of graphs. This is what is known as the codes on graphs, or graphical methods of encoding or decoding the channel codes, which is actually turning out to be quite powerful approach, not only in the context of LDPC codes, but with some modification, the same techniques also apply to the NOMA detection methods. And also this LDPC decoding methods, again, after some modifications, the basic concept has been applied to compressive sensing as well. And so this is a non-linear detection technique, but it performs better than some of the linear techniques that we have studied. In fact, this SIC technique and even the multi-stage IC, the decision feedback IC, those techniques also, if you recall, we have tried to understand them using the graphical structures. So that was kind of a precursor to a more elaborate iterative decoding techniques that we will cover as a part of this LDPC channel coding and channel decoding topic. So I expect to take maybe 1 or 2 lectures on LDPC codes. Okay, after that I will do, I want to spend maybe 1 lecture on the orthogonal time frequency modulation. And specifically, I want to show how it connects to the OFDM. If you recall, in one of the earlier labs, I had asked you to understand the OFDM technique in terms of the eigenvalue decomposition of the channel matrix. And then I had asked you as an open-ended exercise to see if you can study the OTFS modulation and see how it applies as an extended version of the OFDM concept. So that is something that I will spend a little bit of time on. And after that, depending on how much time we are left with, we will probably do some recap of the MIMO techniques, especially in terms of the signal processing architectures, which are based on the subspace decomposition. There'll be one invited talk by Saket Buch at ISRO. The other by Professor Aditi Tatu was already completed last week. And after that, I don't believe that we will have much time left, but otherwise we may spend some time on studying the performance of the CDMA with SUMF, specifically the system capacity evaluation, and where the objective will be to compare the CDMA against TDMA and FDMA. And there, the main concept that I wish to emphasize to you is the concept of statistical multiplexing. Actually, CDMA, if you do single user mesh filtering, as you may be noticing in lab 4, doesn't perform that well actually. It is one of the weakest detection techniques. But the main advantage of SUMF is that it is computationally, it is the simplest technique. And therefore, there is some merit of studying this SUMF technique with CDMA. And we will show that even with a simple SUMF detection, CDMA has the potential to outperform TDMA and FDMA, because there is something called statistical multiplexing gain that only CDMA can enjoy compared to the other techniques. Okay, so that is in a nutshell the type of topics that we should aim at covering in the remaining part of the semester. By the way, I have given you the extension for this lab. You have little more time to work on it. I did this mainly because you have your stage 1 presentation coming up this week, and I thought this will give you some extra leeway to do a little more detailed work on this lab 4. The next lab that I would like you to do is going to be focusing on this LDPC codes and this belief propagation algorithm. I think it's a very nice algorithm, not very difficult, I think, in my opinion, to simulate and to implement in MATLAB. But once you do that, I think you will get a very good feel of a wide range of this interference cancellation algorithms and so the LDPC decoding will be the next lab of, and probably the final lab of this semester. Into NOMA, and here, so NOMA techniques, as they have been presented in the literature, can be broadly classified into two different types of studies. In one type of study, the one that we are going to be focusing on, the assumption is that the channel coding has done its job the best way it can. It's a simplistic assumption, but it kind of, with that assumption, the concept of NOMA becomes very clear. So that is the focus that we are going to have today. There is another class of NOMA research and NOMA studies which actually focus on what the information theory and coding theory can actually deliver. And that is where, for example, this LDPC belief propagation algorithms come into play. And so this class of NOMA studies actually go down to the nitty-gritty details of making the NOMA techniques work, making sure that the interference cancellation, which we are going to be assuming here, has been done in an ideal manner, whether the actual receiver can deliver that type of ideality, that type of idealness. That is the other class of NOMA studies. When you do this next lab on the LDPC channel decoding, you would be kind of exerting effort on that second class of NOMA studies. In fact, what you are doing right now in lab 4 is also sort of like the second class of NOMA studies, where you are looking at the actual design of the receivers which deal with the interference, and you are seeing what the receivers can do depending on what algorithms they employ. So there the focus is on the actual signal processing algorithms. Now that study and that area of NOMA research is not the one that we are going to be looking at today. Instead, what we are going to be focusing on is, suppose the algorithm has done its job in the best manner possible, then what can be achieved in terms of the overall system capacity. Okay, so that is going to be our focus. And we are going to be looking at a very simple two-user scenario. And our objective will be to compare NOMA with orthogonal multiple access and possibly with CDMA. So that way, the benefit of NOMA will become clear as we make the comparison against OMA and CDMA. And so the three techniques that we'll be comparing, one is the CDMA with the simple SUMF receiver. And just as a recap, note that CDMA is based on spreading the spectrum. And so if I have an information symbol of some duration T symbol, whose inverse is equal to the bandwidth of a particular user, then as you know, and that is what you are doing in lab number 4, this symbol is replaced by a sequence of capital N chips. And these chips are of a smaller duration. T chip is T symbol divided by N. We want to fit this signature sequence or spreading sequence of N chips over the same symbol duration. And therefore, necessarily, the duration of the chip will be 1/nth of the duration of a symbol, which means that the bandwidth became N times bigger, which is to say that the spectrum has been spread by a factor of N. But then after spreading, all the users kind of pile up on the same spread spectrum equal to NB hertz. So that is the main idea behind CDMA. Okay. In orthogonal multiple access, in contrast, the different user signals are not spread, but they are assigned different portions of the spectrum. They individually occupy capital B hertz of spectrum, but because they are made orthogonal, let us say in the frequency domain, and now if I have N users, then OMA ends up using the same spectral width of NB hertz, except now individual signals are non-overlapping. And finally, NOMA is kind of like CDMA and maybe like OMA in terms of the spectrum use. It is like CDMA in the sense that the different user signals are kind of piled up on top of each other, meaning the orthogonality between the signals is not preserved. But this superimposition may not actually require the type of bandwidth expansion that CDMA does. Because the CDMA requires the bandwidth to be expanded by factor of n because each symbol gets spread by this signature sequence of length n chips. NOMA says that we won't even use any signature sequence. And we will still overlay the spectral occupancies. And so NOMA is that way kind of unique. It can use FDMA, TDMA, or it can even use OFDM, where the individual subcarrier of OFDM, in the conventional OFDM, each subcarrier transmits only one user symbol. Whereas NOMA says that on a particular subcarrier, I will transmit maybe 2 user symbols or 3 user symbols. So there is that type of ambition there in NOMA in some sense. I mean, your typical thought would be, how can you do that? I mean, you can't add multiple users symbols on the same OFDM subcarrier. But we will see how NOMA achieves that. So NOMA is that way kind of a paradigm shift. I would say the basic ideas of NOMA were present for a long time, maybe last 15, 20 years, when the NOMA ideas were, the ingredients of NOMA were formulated. But still, I think it took quite a bit of almost, I would say, revolutionary thinking for the researchers to say that no, NOMA is a viable technique, because otherwise mainly either the CDMA or the OMA were the main focal points. And so that is what you see. In 2G systems, it was either OMA, GSM uses OMA. It uses combination of FDMA and TDMA. The 2G system, which was pioneered by Qualcomm, which is called IS-95, uses CDMA. And CDMA specifically with SUMF receivers. So 2G was based on 1 and 2. When you go to 3G, it was still continuation of 1 and 2 only. Even 4G was mainly number 2, OMA, where instead of using FDMA and TDMA, 4G systems, specifically the LTE, uses OFDM as the transmission technique. So all the way until 4G, the industry and the research focus was on number 1 and number 2. But then starting maybe about last 10 to 15 years is where NOMA started gaining more attention. And specifically over last 5 years is when I say that suddenly NOMA has taken a big leap forward. That now for 5G, it is now considered as a replacement of the OMA. Okay, so let us look at some analysis of this NOMA as compared against OMA and CDMA. And what I'm going to show here, the graphs I have generated myself, and they are not very difficult. You can easily program them in MATLAB. And I believe that Anudeep is very much familiar with this. I don't know if Anudeep is here today or not, but he has, I think, also developed some of these graphs in MATLAB. But the main argument, the main concept that we are going to study today, first appeared in a very nice, easy to understand manner in this textbook by David Say and Vishwanath. And here I'm pretty much going to summarize the discussion in this textbook. So I think you should go and read this textbook also to gain little better familiarity with this concept of NOMA. Okay, so before we proceed, I thought that let us draw the diagrammatic representations of these three techniques that I just mentioned. And because we are going to consider just two users, here is the spectral diagrams of the user signals. So both the users, we will assume that they occupy bandwidth of B hertz, and their power spectral densities look like this. Let's say they both have the power of P watts for every hertz of the bandwidth. So this is how the individual users' signals look like. Now, in CDMA, two users will be spread by, let us say, a factor of 2. So individual spectrum became wider. They became of length 2B hertz. And possibly by doing that, you can reduce the power by a factor of 2 per hertz. And so user 1 signal became having a power spectral of only P over 2. User 2 also has a power spectral of P over 2. But now, because they are kind of superimposed on the same bandwidth, the total power per hertz is still roughly about P watts per hertz. Okay, so that is what the CDMA does. I want to mention that this diagram is probably a little bit misleading. It is not that user 2 power spectrum begins from P over 2 and it goes up to P. I think that would not be the right way to read this diagram. Obviously, both user 1 and user 2 signals, if you look them individually, their power spectral density has a height of P over 2 only. But when you consider them combined, then the net signal has a power spectral density of E watts per hertz. Okay, so this is the concept of CDMA. In OMA, the signals are not expanded in bandwidth, but they are still made orthogonal, meaning that they occupy two different parts of the overall bandwidth. The overall bandwidth still remains 2B hertz, 2 times the individual bandwidth. But user 1 occupies one part of that spectrum, user 2 occupies the other part of the spectrum. And we can say that in this particular illustration, the bandwidth occupancy is 50-50. The sharing factor is 0.5. So this is the OMA. One would say that this would be typically the case for the frequency division multiple access. But in general, I haven't very specifically said what these user 1 signals are. Instead of considering these signals as a sequence of symbols, which would be the case in FDMA, if I consider them as individual symbols, then this would be more in line with OFDM. So that is what this diagram illustrates. It is applicable to both OFDM and FDMA. It probably is not applicable to TDMA as much, but because TDMA doesn't partition the overall bandwidth in this manner. But the concept remains similar, that the two different user signals are made orthogonal. They are made actually strictly orthogonal because they occupy different portions of the available resource. And finally, in contrast, in NOMA, these two user signals may or may not be spread. If they are spread, then the spreading may not be full 2 times B hertz, first of all. But first of all, I mean, let us say that suppose even if they are not spread, NOMA still kind of is like CDMA in the sense that it superimposes the two user signals on top of each other, except that it allows the two user signals to occupy different power levels. And now the power separation is determined by these coefficients beta 1 and beta 2. For example, user 1 signal may be having maybe allotted a smaller power compared to user 2. Okay, so this is the kind of a graphical representations of or illustrations of what I just mentioned on the previous slide. Okay, so what is the magic? How come NOMA do something which the OMA and CDMA techniques said that it is not doable? I mean, obviously, you can see that this is the best way to do the multiple access because you are using a smaller chunk of bandwidth. Basically, you are improving the bandwidth efficiency. And so that is obviously the desired objective. But that objective in the earlier technology was not considered as something that is feasible. And that is why the earlier technologies, CDMA and OMA, ended up using more bandwidth than maybe what NOMA uses. So how did NOMA achieve something that seemed impossible to the designers of OMA and CDMA? Okay, the main argument of NOMA is the channel coding argument. What NOMA says is that, and maybe what NOMA says, unlike what CDMA and OMA designs do, unlike CDMA and unlike OMA, NOMA says that, well, you know, all the communication systems these days use channel coding. It's never almost the case that the signals are transmitted without some type of channel coding. If you consider CDMA, for example, it is purely a modulation-centric technology. And that you would know, given this lab 4 that you're doing. There, currently what you're doing is completely disconnected from channel coding. You are not making use of any channel coding at all. So the CDMA design, and similarly the OMA design also, when you do OFDM, there again, the OFDM technique is purely the modulation technique. Or FDMA or TDMA, they are entirely the modulation techniques. They do not leverage the channel coding methodologies that are present at the communication transceiver. And so if I build a wall saying that my multiple access cannot leverage the channel coding, then yes, I probably am forced to either go with CDMA or OMA. But NOMA said that why? Why can I not make use of channel coding to do multiple access? And so that is the main idea, that NOMA says that I will make use of the channel capacity formulation. Why can I make use of channel capacity formulation? Because I will assume that this channel capacity, which is given by this formulation, which we are familiar with, I will assume that it is attained by either the LDPC or the turbo codes. And in general, even if it is not attained, suppose the channel code is not powerful enough, maybe it's a weak LDPC code or a weak turbo code, or maybe it's not even LDPC and turbo, maybe it is a convolution code, or maybe it is some other Reed-Solomon code. And so I may not be able to attain the channel capacity, but still I will come close to that channel capacity bound. But fundamentally, I'm going to assume that as long as I transmit the information at certain rate, that rate may be very close to this rate C, or it may be maybe less than C, but kind of approaching this channel capacity rate of C, then Shannon's information theory arguments promise to me, and the actual practical channel coding exhibit this, that the information transfer occurs with almost no errors. The actual channel introduces errors, but then this channel coding technique overcomes those errors. And so my communication happens almost error-free. Right? Why is this important? Well, it is important because if I can say that my data transmission has happened error-free, then I can apply SIC in a very effective manner. You know today, based on your MATLAB simulator, that the SIC works very well, provided that in that successive interference cancellation, it has been able to decode the earlier user signals in an error-free manner. Right? If the decoding of the earlier users is error-free, then SIC can completely eliminate the interference from those users. In lab 4, you will find that SIC does not work well all the time. And most of the time it doesn't work well is because the earlier users themselves have decoding errors. And the reason they have decoding errors is because you are not using channel code. But if you are using channel code, and if that channel code is able to clean up all the errors, then actually SIC will work very well. And so that is the main paradigm shifting idea that NOMA brought about. The main idea is still of successive interference cancellation. But the added twist is that SIC is performed in conjunction with channel coding. And then there is one more subtlety that I would like you to fully understand, that the NOMA analysis says that this channel coding will provide almost zero errors, meaning the probability of bit error will be near zero. But in order to achieve that, I cannot exceed this rate. and we are almost always going to focus on the normalized rate, C divided by W, which is nothing but bits per second per hertz, which is same as the spectral efficiency, which is also same as bits per channel use, whose formulation is nothing but logarithm of 1 plus SNR. So that is a key argument of NOMA, that if I can control my transmission rate so that it doesn't exceed this log base 2 of 1 plus signal power divided by the noise and interference power, then I can ensure that in the successive interference cancellation, the decoding errors are zero, and therefore it works very well in cancelling out all the interference. There is one additional caveat that for this channel capacity bound to hold, the noise and the interference have to be assumed to be Gaussian distributed. The noise is fine. We can assume that noise is Gaussian distributed. Interference, whether it is Gaussian distributed or not, is a question mark. Especially if we are considering only 2 users, maybe we cannot always assume that the interference is Gaussian distributed. If the users are using, for example, QPSK modulation, I don't know whether QPSK modulated signal has Gaussian PDF. So there is some simplification in the argument there. But fine, so if you cannot fully attain the channel capacity, the argument doesn't fall apart. Only thing that happens is maybe you have to reduce some of the data rates that we are going to be now looking at. Okay, so that is going to be our main line of attack. This is what we are going to be doing now. Okay, so with that, let us consider the details of the analysis. In order to exhibit the performance gain of the NOMA over the OMA and CDMA, we are going to consider that there are only 2 users present. This simplifies the analysis, and it also conveys the concept in a very nice manner. But we have to keep in mind that this is definitely a simplified situation. In reality, there will be always more than 2 users. So we are going to define the power of user 1 signal as it is received by the receiver as PRX1. And similarly, PRX2 is the power of the user 2. And Pn will denote the power of the noise. Now, one assumption that is going to be made is that the transmitters of both the users know what these levels are. So this is kind of an ideal assumption. You know, the transmitters, yeah, fine, they will know what the power they are transmitting at, but how do they know the power at which the transmit signal is getting received? So in reality, we will have to make some system design so that the transmitters know what these received power levels are. And here we are just going to assume that that design has been implemented, and somehow the transmitters know the levels at which their signals are reaching the individual receivers. Now, once the transmitters know these power levels, then they can plug those power levels in this equation. PS will become the power at which the signal has been received. And so based on that, the transmitter can calculate the channel coding rate C, and we are going to assume that then the transmitter is going to pick up the appropriate channel coding scheme so that it transmits the signal exactly at that rate and not above a rate given by that channel capacity bound. So that is the assumption. Now in NOMA, the analysis differs a little bit when we look at the return link compared to the forward link. Return link is the link from the user terminal to the base station. And there, the individual user transmitter are transmitting kind of in an independent manner. The forward link is the link from the base station to the user terminals. And there, the signals going towards different user terminals, they are kind of conjoined in some sense because they're all transmitted by the same power amplifier that the base station transmitter has. And so there is certain power limit that is present that acts as a constraint for all of these different user signals. So we'll be looking at the return link first, and then we'll go to the forward link. Okay, so I'll take a momentary break, and then I'll be back. Okay, so let's continue. So in this analysis, basically we are going to look at the type of data rates that can be achieved in these different multiple access techniques. So let us first consider CDMA. And specifically we are considering the single user match filter. And so there you will note that user 1 receiver will see the noise power P of n, but because it is single user, it sees the user 2 signal completely as interference. And it is making no attempt to remove this interference. It is not using any of this decorrelating technique or any of the SIC techniques. So the total noise power that it sees is Pn plus PRX2. And similarly, user 2 sees a noise power of Pn plus PRX1. Okay. What about orthogonal multiple access? Well, let us assume that the bandwidth allocation is in the proportion alpha and 1 minus alpha. Recall that in that illustration, I had made alpha equal to 0.5. So both the users were using 50% of the overall bandwidth. In general, that doesn't have to be the case. And so that can be any number alpha between 0 to 1. And what happens is that because you are dividing the overall bandwidth in this proportion, the noise power that the two users see is also getting divided by the same proportion. So what I'm trying to say here is that in the OMA, the noise power is present over the entire bandwidth of 2 times B hertz. But user 1 will see only half of that noise power because it will, for example, it can put a filter around minus B to 0. And so the noise power which is present in the spectral band from 0 to capital B will be nulled out by that filter, in addition to user 2 signal. So you can see that the power as seen by user 1 is going to be only half of the total noise power. That is the case because alpha is 0.5. If alpha was 0.25, then user 1 will see only 1/4 of the total noise power, and so on. So that is the statement that we are making here. That the noise power in the OMA is going to be divided in the same proportion as the bandwidth is. Now in NOMA, because it will use the SIC method, we will say that user 1 is decoded first, and in this decoding, user 1 is going to use just the SUMF. And so it will see the full interference from user 2. And so it will see the effective noise power, which is same as the CDMA, PRX2 plus PN. But now, because of this SIC, user 2 is going to completely get rid of the interference coming from user 1. And so therefore, user 2 will see just the noise power of PN. It will not have any interference component of PRX1. Okay, so that is the main idea that we are going to be using. Okay, so let us see the actual formulation. For NOMA, as we said, user 1 is decoded first, and then user 2 is decoded after that. So user 1 sees the total noise power of PRX2 plus PN, and its own signal power is PRX1. And so the rate at which user 1 can transmit is this rate, log base 2 of 1 plus PRX1 divided by PRX2 plus PN. This is, by the way, the normalized rate in bits per channel use. Remember, we have said that the transmitters know this PRX1 and PRX2 values. So user 1 transmitter, it will calculate this quantity and it will use the appropriate LDPC or turbo coding whose rate meets this inequality. And therefore, the total data transmission rate in a normalized sense, user 1 transmitter will make sure that it does not exceed this limit. Here we are going to just say that the turbo coding or LDPC coding is ideal and it can deliver exactly this channel capacity rate. So we are just going to assume that user 1 will be transmitting at R1, which is equal to this log base 2 of this quantity. Now, because user 1 is transmitting at this rate, its receiver, the channel decoder, will be able to operate in a completely error-free manner. And so user 1 signal will be decoded without error. Because user 1 has been decoded without error, it can be entirely eliminated from user 2's detection process. And therefore, user 2 now can transmit at this rate. Obviously, we can decode user 2 first and then user 1. Then the only thing that changes is this PRX1, PRX2, they get interchanged. So this is the rates that are achieved in the NOMA. What about CDMA? Well, in CDMA, we say that user 1 sees the interference of PRX2 plus PN, same as NOMA. But then user 2 also sees interference of PRX1 plus PN. And so this is what the CDMA can provide. Finally, let us look at OMA. Remember, in OMA, the noise power gets smaller by a factor of alpha. And so, oh, by the way, there is first of all no interference. So the denominator has only the PN term. Furthermore, the PN term itself is getting reduced by the factor of alpha for user 1 and 1 minus alpha for user 2. So this quantity is actually much better. It's even better than NOMA. The noise power does not have any interference at all. Plus the PN term itself is getting reduced. So that should help. The problem is this logarithm sign in front of this bracket. So the benefit that you get by removing the interference and scaling the noise power, it gets attenuated in some sense. It gets kind of compressed because this log is a compressing function. It's an opposite of exponential function. If you put something inside the bracket of a logarithm, what comes out is a smaller number typically. And so, yes, you get benefit by removing the interference and by scaling the noise power, but this log base 2 kind of attenuates that benefit. But then the bigger problem is that outside of log 2, you get hit because now there is a factor of alpha and 1 minus alpha that gets multiplied. The log function gets multiplied by alpha and 1 minus alpha. Can anyone tell me why this multiplication happens? Alpha and 1 minus alpha?
So the bands are orthogonally divided, so the power spectrum is separated into alpha and 1 minus alpha times the whole power spectrum. Noise power spectrum, PM.
No, that is here. The noise power spectrum gets separated out in the same proportion, alpha and 1 minus alpha. That part we already accounted for by scaling Pn by alpha and 1 minus alpha. My question is, what is the reason why I put alpha terms here, outside of log base 2?
Sir, because the entire bandwidth is divided into by the proportions of alpha, so the
Correct.
rate is also dependent on alpha.
Yes, Divya, I think you hit the nail on the head. Remember, the actual channel capacity formula is this here. C equal to W times log base 2. And I've told you that what we are going to be interested in is the normalized C divided by W. Now, once I normalize, I don't have to worry about what the exact value of W is, except in the OMA, I still have to make sure that if I use the alpha portion of W here, then that alpha remains as a multiplier of this normalized C divided by W. So that is where this OMA multiplier of alpha is coming from. And you can argue that although OMA gains a lot inside the logarithm bracket, you can argue that it more than that, it loses up, meaning the benefit that it accrued inside the logarithm brackets probably gets more than compensated because it takes a hit outside of the logarithm bracket. because this alpha here and 1 minus alpha, they are not getting attenuated. And so you have to live with the full effect of alpha and 1 minus alpha. And so maybe that is the reason why OMA, as we will see, it will underperform NOMA. Now, as a system designer, we want to know what we can achieve overall in terms of the overall system rate. Individually is also important, but overall what we are able to do. So that is what we are going to look at. We are going to see what R1 and R2 together can be. Remember,
Sir,
yeah,
sir, so suppose CDMA is having this knowledge of R1 and R2 at the transmitter, and it uses a good enough channel code, it can work much better than NOMA, right?
no. So this is assuming that CDMA also uses channel coding, and that's why it can do R1 is equal to log base 2 of 1 plus PRX1 divided by PRX2 plus PM. The point is that because it is using SUMF, it is not attempting to get rid of this PRX2.
Okay.
So
How about CDMA with SIF, SIC?
that is NOMA here. So this is CDMA with SIC, but it doesn't even have to be CDMA. All that we are assuming is that the user one transmitter, whether it is CDMA, whether it is OFDM, whether it is TDMA, user one transmitter sends the signal at this rate. And user 2 transmitter therefore can send the signal at this rate, R2. Compared to CDMA with SUMF, where R2 has to be smaller because the interference from user 1 has not been removed. Okay, does it answer the question?
Sir, I'll ask later.
Okay. Maybe as we go along, maybe some of this doubt will become clearer. So what I'm going to do now is to draw the system capacity diagrams. And this might be a little new for you, but I think that is why we are considering only 2 user case. If I start drawing this type of diagrams for 3 users, they will become very complicated to draw. And above 4 users, I don't think I can even draw it. But for 2 users, I can draw the capacity diagrams. By the way, yeah, the important part is that the overall system capacity, which is R1 plus R2, is obviously going to be limited by this log function, where the total signal power is PRX1 plus PRX2, and the noise power is Pn. Sorry, I used the wrong notation. The sigma n squared should be Pn. They'll make the change right away. Okay. So this is how the overall system capacity diagram looks like. X-axis is R1, Y-axis is R2. Okay? And what I'm showing as of now is what the NOMA can do versus what CDMA can do with power control or without power control. So how did I draw this diagram? Remember, we are saying that user 2 signal is getting decoded first. And so user 2 can get a rate of log base 2 of PRX2 divided by PRX1 plus PM. This is same as CDMA. And so this point here is same as CDMA. Why is this 0.585? Because I'm assuming that all the signals are at the same power. User 2 and user 1 signal are at the same power, and that power level is same as noise power, meaning that all the users have an SNR of 0 dB. PRX1 divided by PN is 1 divided by 1, which is 0 dB. PRX2 divided by PN is also 1 divided by 1, so it is 0 dB. And so if I plug those numbers in this equation, I get log base 2 of 1.5. 1 plus 1 half. And if you do log base 2 of 1.5, you get 0.585. So that is this value over here. So this is what the user 2 of NOMA and user 2 of CDMA, they will do. They will be able to get a net rate of 0.585 BPCU. But now, this is where the NOMA will outperform CDMA, because as we said, because user 2 is transmitting at this rate, its signal will be perfectly decoded using channel decoding. And therefore, the SIC will work perfectly for user 1. And so user 1 will not see user 2 interference at all. And therefore, it will be able to transmit as if it was the only user present. And so it will be able to get a net rate of 1 BPCU. And so using NOMA, I will be operating at this point here. Are you able to see my cursor? Yes, no?
Yes, sir.
Yes, sir.
So using NOMA, my system is operating at this point. Whereas with CDMA, I'll be operating at this point. Does this make sense? By this point for CDMA?
Sir, because the power levels will be same.
Yeah, no, power levels are the same. But why NOMA goes all the way here, whereas CDMA is stuck here?
So because power levels will be same, then we'll be able to substitute these values. How we have obtained 0.5855.
Okay, Arushi, what do you think? Why did I put CDMA point at this location? Arushi? No, you are not audible. You can type on the chat window. Do you know why I put the CDMA capacity point at this location? Exactly. So Arushi has given the right answer that in CDMA, remember, user 1 will have almost the same data rate expression because it sees the interference from user 2. And so once I substitute the values, I'll get 0.585 as the user 1 data rate. And so the coordinates become 0.585 and 0.585 for user 1 and user 2 for CDMA. Whereas for NOMA, they become 1 and 0.585. So NOMA operates over here. Okay, who is next? Joel has spoken, Arushi has spoken. Bhavesh, a question for you. Instead of decoding user 2 first and then user 1 in NOMA, if suppose the receiver at the base station, remember this is on the return link. This is not forward link. This is the return link. So the base station can decide whether to decode user 1 first or user 2 first. Suppose if the base station decides to decode user 1 first and then user 2, where will the system operate at in this diagram?
So that above the pink dot, the one
What is the coordinate? What is the x coordinate and what is the y coordinate?
0.585, 1.
Okay, exactly. So if the ordering is switched, the NOMA will operate over here. Okay, so that is what this diagram shows. This would be the case when the ordering of the SIC is switched at the base station. And so in general, NOMA will allow operation at actually any point along this line. Why can I not draw a full square? That is because I cannot violate the information theory limit. The rate R1 plus R2 cannot exceed this total rate limit. And so this is the maximum that you can get in terms of the net system throughput. The point is that NOMA with SIC can actually be operating at any point on this slanted line. We already saw how it can operate either at this vertex or this vertex of this pentagon. But by appropriate power scaling, we can allow the NOMA to operate anywhere over here. And so you can see that NOMA is strictly better than CDMA. Okay, so let us continue. What about OMA? The OMA formulation I have already given you earlier. There, because of that alpha multiplier, the overall system capacity points, they trace out this type of curve. This is very easy to program. You can do it in 10 minutes. If you plug in this formula here in MATLAB and change alpha from 0 to 1, then you will get that green curve. Okay, who is next? Okay, Kishan, can you tell me this point here on the green curve where my cursor is, what is the corresponding value of alpha?
Sir, alpha is 1.
Yeah, no, actually, remember this y-axis is user 2.
Achha, so it is like 1 minus alpha. So it should be 0, right?
Correct. So for this point, alpha of OMA is 0, meaning that the entire bandwidth has been allocated to user 2. And so user 1 gets a rate of 0. We haven't given user 1 any bandwidth at all. Whereas for this case, alpha is 1. Now user 2 doesn't get any data. This point here corresponds to alpha equal to 0.5. So you see that quite surprisingly and maybe a little bit non-intuitively, even when these signals are equally powered, the OMA underperforms the NOMA. If you are looking at the overall system throughput, how both user 1 and user 2 can maximize their data rates, then obviously you would want to operate at this blue pentagon rather than the green curvature. Except if you make alpha equal to 0.5, then the OMA and NOMA will give you the identical performance. But for all other values of alpha, it is better to go with NOMA. Okay, this is the case when the signals are equally powered. Now let us assume a case when user 2 is 6 dB greater than user 1. Okay, so the user 1, we are still going to assume that PRX1 is 1, PN is 1, but PRX2 is 6 dB greater than user 1 signal. So now the pentagon looks like this. Sorry. And the OMA curve looks like this. How did I get 1.58, 0.58? All this you can calculate yourself very easily by just plugging in the formulas. The point that I wish to make here is that now there is a difference in the CDMA whether you do power control or you don't do power control. Remember, in the conventional CDMA, power control is considered necessary to avoid the near-far effect. So what happens is that if I do power control, then I will have to bring the stronger user at the same level at which the weaker user is. Basically, I will have to ask the user which is close to the base station to attenuate its transmit power so that the signal of that user is received at the base station at the same level at which the weak user signal is received. Right? I mean, the other alternative would be to ask the weak user to transmit at a greater power so that its signal is received at the same level at which the user wants the nearby user signal is received. But that is not possible because user who is at the edge of the cell, edge of the sport beam, is probably already maxed out. He or she is already transmitting at the max power level that its device can allow. So we cannot ask that user to increase its power. The only possibility we have to do power control is to ask the nearby user to attenuate its power. And therefore we get this rad square. But rad square is highly unfair to the strong user. Actually, if this weak user was not present, the strong user could get a capacity which is as large as 2.32 bits per channel use. But just because this weak user is present, and we are asking user 2 to be a nice guy, basically it will have to be satisfied with a rate which is roughly about 1/4 in this case. On the other hand, if we don't do power control, then the problem is that in CDMA, yes, user 2 will get a higher data rate of 1.58, but user 1 will suffer because we are not doing power control. So in case of red, user 2 is unhappy. In case of pink, user 1 is unhappy. However, look at this NOMA. In case of NOMA, if I suppose decide to operate at this vertex, user 1 is going to be super happy because although it is the weak user, although it is a disadvantaged user, although it is located at the edge of the cell, and it knows that there is this higher power interferer which is present pretty close to the base station, it is able to get a data rate as if there was no interferer at all. It is able to operate at its max data rate of 1 BPCU, which is what it would get in the ideal scenario. And furthermore, user 2 is also not that unhappy because it is operating pretty close to what it can get, the maximum value of 2.32 it can get. So this coordinate point 1 and 1.58 is a pretty good compromise. It satisfies user 1 and it doesn't penalize user 2 that significantly. One can do OMA, but then user 1 will get penalized. And so again, there are areas of this capacity diagram where NOMA is better, significantly better compared to CDMA, and even definitely better compared to OMA. And OMA can provide the optimal answer, but that optimal answer forces us to use a specific value of alpha. And the situation becomes even more dramatic if the power levels are 12 dB apart. Now, CDMA with power control is very bad. Without power control also is very bad for user 1. And now it is looking more and more likely that we would go with this particular operating point of NOMA, where user 1 gets full data rate of 1 BPCU and user 2 gets 3.16, which is not that bad compared to 4.07, which is the maximum it can get. So looking at it side by side, we can say that when the power levels of the two users are mismatched, which is the near-far problem, in CDMA, until the advent of NOMA, near-far was considered a problem. And it was considered something that was a headache, and therefore there was a lot of design of power control that happened. A lot of dissertations were written on CDMA power control. A lot of implementations happened at Qualcomm, at Broadcom, at Nokia, Ericsson, everywhere. NOMA came along and said that, okay, just trash all of that power control. Actually, near far is not a problem. Near far is actually a good thing. We can make good use of near far effect by making user 1 actually very happy. Although it is very far, user 1 will be very happy and user 2 will be okay. User 2 will not be severely disadvantaged. CDMA cannot simply do that. OMA can achieve some optimal operating point, but at that operating point, maybe the weak user will not be very happy. So NOMA actually provides kind of the best of the both the worlds. So in summary, on the return link, the non-orthogonal multiple access can provide a system capacity advantage, especially in the case when the near-far effect is present. And a good strategy would be that the user which is closer to the base station, it will, in the decoding order of the SIC, it will be the first user to be decoded. It will just apply the regular single user match filter. On the other hand, the weak user will first decode the stronger user from the net composite signal, and then it will use SIC to remove the interference from the strong user, and then it will decode its own signal. And so by doing that, the weak user can operate close to its maximum throughput because it will not see any interference. Whereas the strong user has to give up only a little bit on the data that it can achieve. The reason it has to give up only a little bit is specifically because the other user is weak. And so even when the strong user doesn't do SIC on the weak user, it doesn't lose much, because the weaker user obviously cannot interfere much with the strong user. And so now the NOMA with the SIC performed by the weak user can give you a system performance which is going to be better in terms of the overall throughput, as well as in terms of the fairness to both the users. If you say that these two users have the same power level, then the case for NOMA kind of diminishes. Then one can say that, well, OFDM is probably okay. You don't have to do NOMA. And the case for NOMA diminishes because OFDM is better in terms of implementation. You don't have to do any interference cancellation because there is no interference. And so what you would do is just divide the bandwidth in equal proportion, 50-50, and then you will get the total throughput, which is the best that can be attained from this information theoretic perspective. But in most situations, you will have more likely a case where one user is close to the base station and the other is far away from the base station. The chances that both the users are at equal distance from the base station are probably smaller compared to the chance that the two user signals are mismatched in power level. And so in such cases, the NOMA is going to be better. Okay, so I think let us stop here for today. We have just completed the discussion on the return link. When we meet again on Wednesday, we will do the remaining part of the discussion as it relates to the forward link. And there also we will see that NOMA is actually able to outperform the OMA.